Proof by exhaustion. In proof by exhaustion, you try all possible given options. This is from the exam board. So in this example, we have a set of natural numbers less than 50, and we have to show that there are fewer square numbers than prime numbers, which means all of the possible options are all of the natural numbers less than 50. We need to consider all of them. So these are all of the square numbers less than 50. There's 7 of these. Now there should be more prime numbers than these square numbers. So I'm looking for more than 7 prime numbers. There are 15 prime numbers. So this is proof by exhaustion. We're looking at all of the options. So all of the numbers 1 to 50 have been considered. In this example, we consider the odd positive integers less than 7. So that's 1, 3 and 5. It doesn't include 7, it says less than 7. So x could be 1, 3 or 5, and y could be 1, 3 or 5. And it says it's a sum. So if I put the numbers into a grid, and the numbers in red represent the sum of x and y. So for example, if x is 5 and y is 3, their sum is 8. And these are all even sums, which we have now proven, and we're considering all possible options. Hence proof by exhaustion. So we have to prove by exhaustion that the sum of the first n consecutive integers, positive integers, is given by this formula, and the options are these. For the positive integers 1 to 6. Okay, so I've done them all here. So 1, 1 plus 2, then up to 3, 4, 5, 6. So let's, if we take this particular option as an example. So in here, n is 5. That's the last value. N is 5. So it's saying in the formula it should be then 5 times 5 plus 1 divided by 2. So 5 times 6 divided by 2. So that gives 15. If you work this out, it gives 15. And if you add these numbers together, they also add up to 15. So we have proven this for all positive integers from 1 to 6. In this example, we consider all integer values in this interval here. So our options would be n equals 2, 3, 4, 5 and 6, but not 7, because n is less than 7, 7 is not included. And for those values of n, we square them and add 2. The result should not be a multiple of 4 for these n values. So when n equals 2, 2 squared plus 2 is 6. That's not a multiple of 4. When n is 3, 3 squared plus 2 is 11, not a multiple of 4. And the same thing's true for n equals 4, 5 and 6. None of these are multiples of 4. So we have proven by exhaustion this statement.